So today the topic is movement in confined space. It actually fits nicely after having listened to Otto. He was talking about heterogeneous space. Now this is a special case of heterogeneity because it's confinement. So somehow, you know, the advective term that Otto was talking about, this B of x, you know, it's a sort of a force where the animal, you know, he was showing this graph like this, no, versus space, no? And so now if you have a boundary which keeps you inside, then these forces actually is something that becomes infinitely strong, no? At some point, so you never escape. So, and if inside these boundaries you have heterogeneity, then of course you are going to have some hills and valleys and so on, which represent this force. But if you, on the other hand, is like you'll see the data that eventually for the final exercise would be about a rat moving in a circular arena in a lab. So the actual space is really homogeneous inside, and then you just have this boundary. So you have something which is really like this, no? So the advection, in some sense, in this way, is just here, no? Only at the boundary. So just to fit it into with movement in heterogeneous landscape. Now, so far what we have seen is what we have learned yesterday was there is a general way of representing a correlated walk through a memory of the walk, which has an average time for which you go straight, the key, capital T. You've done the exercise, and then you have the speed of the animal, which is v. So these are the two parameters you need. Now, this is, if you want, the more macroscopic description. And the microscopically, we have found out doing the simulation yesterday. And what I told you yesterday, what is the relation between T and the turning angle distribution? So we wrote it yesterday, was through the log of the integral of the mean cosine. And so the Q of theta is the turning angle distribution. So you connect a description which has macroscopic parameter, your average speed, your average time you go straight, to a microscopic description, which is the one you use to do the simulation, which is the turning angle distribution. Have you done the exercise yesterday? Q of theta is turning angle distribution, sorry. Minus pi to pi. What did you do? Tell me. Yeah, no, but you are integrating over a random variable. Yes? Yeah, it's the average time for which you go straight. Average, but that's right. Well, because it's connected to the cosine of the turning angle. The cosine is a projection along your direction. So if you, as I told you yesterday, if you keep going straight, you have a turning angle distribution which is just a delta function at 0. So this you're going to have a maximum of this value, and then this becomes actually is a 0, so then your log gives you infinity, so you go straight forever. And so you have a ballistic case.
In terms of units.
Yeah.
So there should be the velocity should be included in the numerator.
Yeah. So I mean, you make. So here the unit here is, yeah. There is a factor here. There is a factor. I mean, there is a whatever some units of time. Let's say a units of time. Okay, which is, you know. So, you know, when you're doing the simulation which are discrete time, that's your, you know, whatever that discreteness you assign to the simulation is whatever comes out here. So this is what you found out yesterday. Now, what is going to be different from today, since we're talking about confinement? Yesterday, there was no spatial scale, really, because the system was unbounded. Now there's going to be also a spatial scale. So we are a sort of a temporal scale. Now we're going to have a spatial scale. And interesting things are going to happen. So I want to show you first a little movie here about the data that I want you to analyze. And I don't know yet what I want you to analyze. I'll figure out this afternoon. This afternoon you have to do the other exercise, which I've written it out. But for the fourth, let me think yet. But the data are the following. So these are data of, now the geometry here is the circular one. So you have rats. They move in a circular arena. They're searching for food. So there are these food pellets which are dropped from above, and since they're dropped in kind of random fashion, then they fall in some sort of random way. And these rats, the position of the rats is recorded over time, and it's actually a very precise position because they have a sort of a LED, and so there is a camera on top, so attached to, I think it's for the neck, so they know exactly where it's going.
How big is the arena? How big is it?
It's 1 meter diameter. So now, so let me show you the movie, and let's see. Now that you've done the exercise yesterday, you are going to tell me what kind of random walk it is. Oh, it's started already.
But they smell the pellet.
Huh?
They smell the food.
There's food?
Yeah, there is a food. Unfortunately, this is a situation, it's a more ecological situation because we don't know where the food, they didn't record where the food was.
But what is their ability to sense from what distance?
Yeah, they have, it's a semi-dark arena, so that because they need a little bit of light for the camera to see what they are looking at, but they have to really search and smelling essentially. But they have some cues, which is related to the fact that when the food pellet drops, there is a little bit of sound which makes them, oh, now I have to search, has come, something like this. So now if I ask you, what kind of walk is this? Now you should.
Correlated.
Very good. I mean, you can see, So.
I can tell you the distribution.
so there are, I mean, the data are 11 of these kind of experiments, so 11 different experiments. I actually don't know if it was the same rat in different days or different rats, but anyway, so they are similar. And so this is the one that eventually you analyze. And I want to tell you what to expect theoretically from this. There is also another step that I'll tell you tomorrow, probably I won't have the time today. Remember, it's a single trajectory. And so far, what have we talked about? Mean square displacement, which is average over many trajectories. So how are we going to deal with that aspect? It's an important issue, which I'll tell you, which you need for the fourth exercise. So I won't have the time today. But anyway, imagine that you have this kind of situation, and now you do another experiment, and maybe the same animal you put back in this position, and supposedly the food is distributed in the same way. Then you just follow it, then it gives you another trajectory, and then you can reconstruct the entire distributional trajectory, so the entire probability function. So the question is, what would you expect?
Okay. Increase up to a mean, and that's it, flat line.
Very good. This is a good intuition, but it's not the right intuition. So I just make fun for you. And now, I mean, let's do it step by step. So, and then, of course, physics is simplified to things which are Cartesian. No? This is very complicated. I mean, we'll do the geometry circular tomorrow, but let me just start with things which are simpler, and of course, we'll be talking about 1D and square lattice, well, a square geometry. So imagine you have this situation.
Can I ask a question?
Yes, please.
How can you be sure that they're looking for the pellets and not just trying to find a way out? Do they have some arbitration to the geometry?
No, they try to, so they're kept in a situation where they're deprived of food. So as they put them in, they really have to eat. So they're really searching. So this is a really search situation. And it's perfect if I would have had the data of where the food was, so that you actually really see the efficiency of search. Then they didn't record that. So
actually, there was a lecture on the last conference, I think, on the Zoological Society in Israel, where they showed exactly the same thing, but without food. They just put the rats in a new space, and they show how they start studying the new space, and it's exactly the same. They start by doing a circle, and then they start studying.
Yeah, so you're right. There is one aspect which I wanted to tell you just at the end, but so if you want me, I can tell you now, which is a biological aspect, which is, you know what's the meaning of thigmotaxis? Thigmotaxis. I forgot if it's a Y or an I here, but a Y, no? So animals, I mean, well, let's talk about the rats. Then there is another general concept of thigmotaxis.
Is it also with students?
With students, and they stay next to the walls.
Yeah, even they're next to the walls, and even they put them in really large spaces where there are no walls. But I don't remember what they did.
Okay. Anyway, thigmotaxis has to do with boundaries. So, and an animal, the rat, especially in this kind of situation, they feel more secure if they stay close to a boundary. So it's it's a sort of a relaxation mechanism. Eh?
It's a line.
It's a what?
Line following.
Yeah, it's a line following. Now, in fact, cockroaches. I mean, this is a more it's more widespread in animals. Cockroaches have done experiments long ago where they actually really see they follow the boundary. So, in fact, you know, there is a great need of developing model, probabilistic model that allows you to say, okay, I have a thigmotaxic animal, so what should I fit? No? And so I'm involved in trying to develop such a model. So essentially what they do, if you think about, in the circular case, there is an area here beyond which you essentially are attracted to. No? So there is that's the heterogeneity now. It's not really homogeneous anymore. No? So there is a sort of attraction. If you really plot the radial probability distribution for this experiment, if I put just the radial, PR, or where they've been after a very long time, what you see that there is something that, you know, essentially it's like this. And this is the value A, let's say. So there is a higher chance of being next to the wall. And if you actually use your data there, I mean, I'm not asking you to do that, but if you actually do that in your data, you'll see that. So, yes, irrespective.
Where does it drop? Here.
Well, I mean, you have to stay in. You can't get out.
That's the boundary of the
that's why
confinement of space.
A.
Okay.
Is it touching the boundary or just or a little bit?
Yeah. I mean, they have some sort of size, not this animal, so it's just a tiny bit before. Yeah. Yeah, there is. Yes. I mean, actually, they try to climb over, so I mean, actually, you can find where they hit. So, okay, just keep that in mind. And well, I want to tell you at the end, because you know, as you do the fit, you don't do a perfect fit of what you see, and this is a reason. So, I mean, a model of thigmotaxis is needed. So this is a perfect paper for you know, movement ecology. So it will appear, don't worry. So anyway, okay, so this is a side story, but let's come back here. So remember, so we have, in one dimension, we don't talk about radius, we talk about the length. And then if, now that you have learned various things about the mean square displacement, so at the end of this, you either be disgusted by the mean square displacement or you love it, okay? So we'll do a test then. And so anyway, so if I plot the mean square displacement, and let's suppose for the moment that you have a random walk, so it's equally likely to go left and right, so no correlation. So we all know that what will happen if I start at the origin here. Well, Or was already saying that. So it's going to be linear because we already understood that. You don't feel the boundary here until sometime if you start at the origin. And then Or said, oh, somehow you get flat.
Yeah, but it should bounce with a limit. They can go because they will not always stay on the line. So sometimes they go in. So it should have some fluctuation around.
Okay. Now it's a good intuition. No, it's a joke. No, actually now it's a good intuition, but it's good intuition for the correlated. Now what happens is that, actually happens is that you eventually reach the saturation. And this is related to L squared. It's actually well, there's a factor here, but it's essentially the size of the box. But it actually goes in a monotonic fashion. So your probability function, if you want, if I plot it over time, your probability function, again, you have your delta function here if you want.
Is that 6 or G? Or what?
6, it's 6. Do you want to know why it's 6? Well, it's just because it's the mean square displacement, remember, it's dx x squared. So x squared, so if you integrate x squared, you get 1/3, and then it's the left and the right boundary gives you the 6 factor. It's not. Anyway, it's just, I mean, it's not important, numerical factor, but it's essentially the size of the box. So if you have your probability function and look over time, then what you see, you see like this, and then as you eventually approach here the boundary, these are reflecting boundary condition that keeps you in, and therefore this, your tail are going to grow, no? And then eventually it's flat. So now if you measure the mean square displacement of something constant, as we said, it's dx x squared. Now this probability, now it's a constant of a space and time. So it comes out here. And what is the constant? It's 1/L, no? It's equally likely to be on the size L, it's 1/L. So if you do that calculation, you see you get L squared by 6. So anyway, what was important to tell you is that you have a linear increase because it's a random walker, but then it saturates to the size of the box. And or actually said it before, it was the right intuition. So that's what you should expect from a random walker. Now, just without going through the detail of the math, the expression for the mean square displacement, if you actually write it down, well, we'll have, it will be L squared by 6, because that's where I had to reach. And then it's completely different than a Gaussian. What we have heard is that a random walker, the probability function is a Gaussian. It's a very nice function, very simple now. Why is it complete difference? You're going to have an infinite series, for n can go from 1 to infinity, of a function, let me just put without, fn depends on time, and then some g n of x. Let me not specify what they are. And these are all exponential functions. There is a diffusion constant, then there is the size of the box. N squared pi squared dt over L squared. So the parameters are here, d and L squared. Now, why is it, so what I just want to tell you is that why is it you have suddenly from a Gaussian an infinite series? Any idea? So the nature of the problem has changed from a diffusion in unbounded space. It's like you have to solve a diffusion equation with boundaries. So as you have a completely different problem. And boundary value problem are always much tougher than initial value problem. So you have a differential equation you have to solve with boundaries. So in other words, our famous diffusion equation has to be solved simultaneously with a boundary. Now, there is no memory here because it's a diffusive case. Now you have to solve also this together with this. The partial derivative space evaluated at x at minus L over 2, let's say, L over 2, the two boundaries. So evaluated at this derivative at any moment in time evaluated minus L over 2 and plus L over 2 has to be 0. So no flux boundary condition. So it's not just a solution of this, it's a solution, simultaneous solution of this and the boundary. Much tougher problem. And not surprisingly, you get something which is a monster here. So you don't have to know how to derive it, you just use it. You see, you have an infinite series. This, I can tell you, are object, so why did I put, this is GNX. There is no GNX, there's GN, sorry. It's a mean square displacement, there's no X, there is only time dependence. So, so you can use it, and if the series decays, if these terms typically decays very quickly. that becomes very tiny after 100 terms, or even less. So if you're in that case, you're lucky. So when you go on the computer, you just sum from n to 100. I mean, that's it. So it's very simple to use, even if it looks awful. So to see why you get the linear dependence, you have to do limits here, which are a bit tricky, but you get it. So why do you get discrete values? Well, this is the nature of the boundary value problem, no? If you have a box and you think about what are the frequencies allowed in a box, they're not all frequencies, only those that satisfy the periodicity, no, of the box. So that's why you get these discrete values. Do you understand? So do you remember this equation? So the way you solve this, you assume that you can separate space and time. These are called the ansatz. So you have a separate solution for the spatial part and a separate solution for the time part. The time part, you say, let's assume it's exponential. That's why you get this exponential. The spatial part is the one you saw yesterday, which is g of x is equal to some constant lambda squared, let's say, the second derivative in space of g of x, because we have a second derivative in space here, no? And now you can ask the question, but what else? The boundary condition. So the derivative of g of x at x at plus and minus L over 2 is 0. Now, if you didn't have that, we saw the solution of this, cosine and sine, no? But for any value of lambda, it's allowed. But now we are imposing this, so it's still a cosine and sine, but what are the values of lambda that you allowed? Well, it all depends on the value of L. And only some discrete values of L will be allowed. That's why you get these n's.
Discrete values of lambda.
Yeah, which are discrete value. Sorry, yeah, that discrete value of lambda, and that's why this n's and this infinite series appears. So it just comes out because you have cosine and sine again, as you would expect without boundary. As soon as you put the boundary, you have only certain value of lambda allowed, and you just, you write the general solution and you impose that this is verified, and you will see that only certain value of lambda are allowed. I mean, that's all. I don't want you to understand more than that. And so that's why you get this monster here. So let's come back here. So here for the random walk. Now let's think about what happens if you have a correlated random walk. First of all, good. A correlated, we have seen it, and we are doing a simulation, it's going to be quadratic there. It's ballistic at short times. First difference. And then at some point, will become linear. And then, and this is question mark. Of course, eventually we'll have to get there, because it's equally likely that it will be all over this arena, whatever the size. I mean, it does depend on the dimension. Now, what happened? But what happened here? So, and you think about, I'm going to draw something. In the case, imagine that you start here, and then you move. And then you have some correlation, so you tend to move there. Imagine you have a very strong correlation. So when you come back, if you are in the ballistic case, all the possible trajectories, left or right, will always come back at the same time.
So you have fluctuation down.
So, exactly. So if you really have a ballistic, what you might expect is that you really have oscillation, because they come back all at the same time to the origin. Any trajectory. No? What is a mean square displacement if you are at 0? 0. And if you all come back at the same time, all the trajectories come back at the same time at the origin, and you compute the average of those trajectories, they're all at 0 at that moment, so it must be 0, the MSD as well.
Like in step number 3 in the first model that we did, over there it wasn't all, but it could be that you either 2 steps away or you came back and then you're in 0, like we had in the first model that we did.
Yeah. So, but anyway, I'm trying to make you think. Okay, before putting the randomness, I'm just trying to make you think the simple thing to understand. So let's think about that they all go out. Now in 1D they just have two directions, so it's easy. But if they are ballistic, so each step they are going to do the same, or symmetrically, and then they come back and they all be there after precisely, given the speed, given the size, and so you are going to have something that comes back, keeps coming back. Huh? Now this is if you have a ballistic case. And now of course you can start imagining, as I'm tuning my parameter of randomness, which we know we can, we just need the t, the capital T different, from here to there, something must join these two behavior, in this MSD plot. So you go from a full oscillation to a damping, total damping. So what you will have? You'll have some sort of dampening of the oscillation. Eventually they will disappear.
To the same.
Eh?
Dumping to the same.
Yeah, to damping to that. Because we know that we expect that.
Damping to that, not with time, with the big T.
Yeah. Well, with no, damping with time, with a little t. Capital T is a parameter. Don't get confused. Capital T is a parameter. I'm talking about time.
I understand that it is the oscillations. If you have the ballistic case, you have continuous oscillation. That's for sure.
Yeah. If you are in the diffusive case, you go to that situation because it's equally likely to be anywhere after some times.
In the middle case, you have damped oscillation.
In the middle case, well, again, I haven't explained you why. I'm just telling you what to expect. You have to bridge the situation. We know that we can bridge because we have the tools we have learned yesterday that they allow us to bridge by just changing the capital T, which is a correlation of the turning angle distribution, to go from what to expect in the ballistic case in this plot to that plot, which is a diffusive case. Let me reduce the correlation, so I go away from ballistic, and then the only way you go from here to there is that you create this oscillation, you damp them out, and of course you also have to reach a value which, if you want, will be an average between the maximum and the minimum.
You cannot go there.
Yeah, no, but this is the average. You can have L squared over 6. Remember, this is L, no? So that's L squared over 6. In fact, you can go beyond that. It's L squared over 6. That's the average. So you can go a bit beyond. So you're going to have to, if you squeeze this, then you're going to be. Now, let's go to the trajectory now to make you really understand. Huh? I'm just telling you what to expect.
Luca?
Yes.
One question. In this analysis, we're talking about a completely ballistic movement. The assumption is that the border is reflective at 180 degrees, but probably in many cases, okay, you could be, now you hit the wall, now you have to randomly select the area, and then you go straight, not directly to the center like where you came from, but another direction.
Yeah, so this you're right. In 2D, you have to, the way to do the simple math is to assume 90-degree reflection.
Okay.
So then, yeah, you're right. So animals may not really do that. So, where I was, okay. So let's go to the trajectory now. And so let's think about what would happen if I start here and then I have strong correlation, but it's not ballistic. So, and then I draw one trajectory. Maybe this trajectory is particularly correlated. So, so there is no switching of direction here. Now you take another one. I just need to use.
Another color.
Yes. So I take another. So this, and it took a time, whatever, T1 to come back. Now I use another color to say that this one actually, oops, there is a little jump, and then it comes back here, and then it took a time T2. So each one will have a different time for which they come back to the origin. So if you do the average at a specific time, which initially for the ballistic were all of them, let's suppose you try to pick that, as you put together, time which are spread out, then you spread out this frequency of resonance, if you want, which is when they all come together, and so you start to dampening this oscillation, you see? So that's why you start dampening this oscillation as you start reducing the correlation, or you go away from ballistic case. as you do that, now, since you are doing that, eventually over a long time, even if you are correlated, since the box is bounded, so you have finite domain, if you wait long enough, it's equally likely to find it anywhere. So you know that you have to expect it to be there. And therefore, the behavior from full oscillation will be damping the oscillation. And why do you damp the oscillation? You know, because a typical behavior would be this one. Why do you damp them? Because, you know, this is, I just draw one situation at short times. But then if you wait long enough, this randomness is going to, you know, accumulate. And so this arrival at 0 is going to be even more spread out. And so you have even more damping. You still have some oscillation, but they get damped out. So it's, I mean, you know, in physics you have this resonance phenomenon. As soon as you're not on resonance, then you know you have this broadening of this arrival, or something happens at the same time. Boom, you have a resonance. And then if they don't, then you have a broadening, and so you have a damping of this oscillation. Is it clear?
Could it be that they come back to resonance after a long time, or it's really?
No, because, I mean, only if they're ballistic. You have seen that after your correlated random walk, after sometimes you forget where you came from. So now here there is, I mean, here interesting is that you have this oscillation because you have a boundary. If you didn't have a boundary, no, you just simply forget where you came from, and that's it.
So it will not hit the 0.
No, so that as soon as you put some, if I let's do it here. If I have to, one case, let's say this is the Brownian case. Let's suppose, you know, we have the ballistic, and then as soon as you put some randomness, then let's say you have something like this, and then you know, something like this. I should have put a different color. Like this. And then as you increase this randomness, you make this distribution of turning angle more and more flat, then, I mean, you slowly reach a situation where you actually are like a random walker. You don't have to really have the, you know, the situation which is a full, the actual random walker, because eventually this damped oscillation, you don't even see them. All clear?
Just to understand the stuff in the ballistic case, so the amplitude is L squared divided by 4?
L squared divided by 6 here in the box. For the box is L squared by 6, this one, yeah.
No, but for the ballistic case.
Oh, the ballistic case, well, the ballistic case, it's probably going to be L squared, this one. It goes all to L squared.
4, because this is the...
Yeah, so you have to, yeah, you probably have to divide by, what would you divide? So you got, what's the maximum that you can get is, yes, yeah.
Okay, not half. When you're saying divided by 6, you're saying that this is L divided by 2, or this is L?
No, when it's divided by 6, it's simply because this is, remember, so this is a size, L is the size of the box, but it's just because you're measuring MSD, which is x squared dx, which gives you this factor 1/3, and then, you know, it's just. Let's see. Oh, okay. All clear? Yeah? So now the question, the natural question, if you have understood this part, of course, I mean, you beg me to explain you, I guess. Now, if we have a parameter which are turning, changing the turning angle distribution, now we have a length scale as well. What is it that's controlling the appearance or disappearance of this damped oscillation? Probably you have already thought about it, but you know, as I'm tuning this, if you have a curve that you can tune at the microscopic level with changing the distribution of turning angles, but now you want to know what are the macroscopic parameters that allow me to tune this from here to there. Well, but the correlation, in some sense, you're talking about, when you talk about correlation, you're thinking about turning angle distribution. I mean, it's true, that's what you're doing in the simulation. But then, I mean, if I would show you this expression, you would know. But what I'll ask, actually, you would not know directly. But what I'm asking is that now there is a length scale. So let me rephrase the question. Imagine that I have a correlation and there is a given box. And then I see this dampening, these oscillations appear. Now I have a bigger box. What happens? I mean, you want to know, no? Same correlation, but a bigger box. Something's going to change, of course. And this beautifully shows up as even just one parameter dependence. Huh? Very good. So, which is the speed L over T. Oh, sorry, what did I do? Vt, yeah, no, sorry. No, there is a length for which you go straight, which is dt, over the length of the box, sorry. So this parameter governs the appearance or disappearance of this oscillation. Now I'm going to explain you why. But so, t is the time for which you go on average straight. V is your constant velocity, whichever it might be. And I mean, the average velocity, if you want. And Vt is the length over which you go straight, on average. You agree? And now you divide by L. L is the size of the box. And so when I was drawing for you all this little simulation here, you know, and what was the appearance or disappearance of this oscillation had to do with the fact that you go and then you come back, no? Yeah, but the way of going and coming back, those oscillations appear if you go straight and you come back, and you divide by the actual space. If the space is larger, if you're stretching this and you have the same type of correlation, then you're going to have less chance of coming back here at the same time, all the trajectory. Because now I'm stretching. Same correlation, so my Vt is not changing. The length over which I go straight is not changing, same correlation, but I'm making box much larger. So all this time, which are different, now they're going to be more different. Therefore, you damp this oscillation even more. And so that's why naturally, this is what you would expect. I mean, of course, I say after I've done the whole thing, but so easy for me to say. But then you would expect that, and then you go in and do the math, the monster math, and then you actually find that. Now, it turns out that despite being the monster math, you can actually, oh, please, yes?
This parameter will also affect the level?
No.
Value.
No.
So it depends on that?
No. No, well, yeah, it affects in the sense on L, yeah, because depending on the box, it affects it. But the dynamics, no. I mean, you still have, but at the actual value, yes, sorry. The actual value, yes. Yes.
Well, if you have a box, it goes to it more than L. L is half the diameter of the box. You go to one of the corners. It shouldn't be L, it shouldn't be something else.
Yeah, I mean, there is a little, I mean, it's, if you want, there is a coefficient which is, I think there is a coefficient there which.
This is one dimensional.
One dimensional?
Yeah, no, this is for the, yeah. This is for one dimension, but you can also do in 2 dimensions.
In 1 dimension, forget about it.
No, but actually, this, remember, this is average quantity, so you would expect some sort of coefficient there, which takes into account all this possible trajectory. I would not expect exactly Vt over L, so I would not expect a transition as Vt over L equal 1, boom. It's something close to Vt over L equal 1, for which you have the appearance of this.
Okay.
But not necessarily, because remember, this is an average value. And then besides, to say when the oscillations, the damp oscillation appear or not, I mean, it's how do you check it now? You have to do visually, no? So you can actually, But one way mathematically to find out, if you look at the details of this expression, is that you can determine precisely when to expect an oscillation to be there or not. And let me know, I mean, you have to do the math. Huh? So, but you see, because there is a root, I mean, there is a square root of something which becomes imaginary or complex. So boom, so that clearly tells you when, which is close to 1. Yes, yeah, no, I thought you were going to ask. So in other words, remember, what do you expect? If, if I make the box very large, so then, okay, this value is going to change, as he pointed out, in terms of where it is on the plot. But then, the box is so large, then it's as if I'm in infinite space, quote unquote. So this effect of coming back to the origin is completely washed out. So for this quantity being small, therefore, because I'm making L very large,
So the frequency gets lower.
yeah, so essentially you go more and more to the situation, you have more and more damping if you want, you go more and more to the situation where you have just a random walk. So in other words, when we talk about a correlation and you actually really have a bounded space, I mean, you have to take into account the size of this bounded space so that you can talk about a correlation being really important and present there or not. If the box is so large and you have some correlation, yeah, you have some movement initially, but that's essentially is diffusive, no, the behavior.
But if it will be very large, so it should be ballistic, it shouldn't be like
yeah, ballistic at short time is always there. Remember that when I was plotting this graph, if you have correlation, it is ballistic. But then the point is that, do these oscillations appear or not? That's a different question.
okay, but if they will not appear, it will continue up.
No, yeah, okay, no, continue up. You don't have this oscillation, but you get this, I mean, you come to the situation where you have this, no? I mean, I was changing L. Now, if you change T, that's the right intuition, no? Let's suppose I change T, I put a lot of correlation, and you fix L. That's the right intuition. I change in T, lots of correlation. That number, fix L, that number becomes large. Then I'm going to go in the situation, I tend to go into the situation where we have all this oscillation. So I increase more L. Remember, T infinity is ballistic. Then I get more and more oscillation. They get less and less damped out. So just, well, it's better not to change at the same time. No, just change T or change L. Cool? Yes, some other question.
I mean, I can understand the importance of the MSD in unconfined space, but in confined space, I mean, what's the meaning of it? Well, you are confined, so what does it matter? I mean, at some point.
I think, okay, let's see. Can I rephrase your question? Let me try to rephrase the question. You may ask the question. Now, I analyze movement data, and I look at turning angle distribution, for example, and I know, let's say, there is an average speed, no? And look at turning angle distribution, no? I mean, and then I know the animal is confined, and then why should I care? You may ask the question, no? Why should I care about learning about MST? I'm going to tell you the answer. Now, if you are in the situation where you know exactly the size of the box, and you just look at the turning angle distribution, and you look, and maybe, yeah, it's equivalent. You just use turning angle and step length distribution, and you know the size of the box, it's equivalent. But if you don't, and this is a more ecological situation, you don't know really what the size of the box is. I mean, what's the size of the home range? Now you have to do the whole statistics, which have all this problem, and determining what the size of the home range. Now here you get, if, on the other hand, you use this method, I mean, of course, you can derive this, but this you use it to get the T, and then if you know the speed, V, and then you're going to determine L. So you're going to determine the size of the home range. But this is out of a time-dependent measurement. You don't do a minimum convex polygon or whatever other method you want to use. You look at the time dependence. You know, all these other measurements are not time dependent. You just wait long enough. Now, the example that I'm giving you in the data, you know the size of the box. So I mean, okay, so that's not really ecological in that sense. So then you can talk about why should I do it. No, of course, I agree.
Yeah, this dimensional number is half of the ballistic case, right?
No, this it's a number. So when you get the ballistic case, remember T is infinity. So this number is infinitely large.
No, I mean in confined space. It's not infinity.
No, remember T can be infinity if you have a ballistic animal.
Moving in the same direction. Moving in the same direction.
Yeah, if you have a ballistic case, T, remember, this is you have a turning angle distribution.
No, in confined space.
Yeah, so but remember.
It must reach the boundaries and then change the direction.
No, but one is the animal and one is the bounded space. So there are two different quantities, which are indeed represented by, let's say, this is the animal, and this is the boundedness. There are two separate things. So you can change one or you can change the other one. Well, if you can.
In the ballistic case,
In the ballistic, remember, the ballistic T, average T, has to do with the turning angle distribution. And if the turning angle distribution is such that you always go, the angle is always 0, so your ballistic, the T values, you can show it from here, becomes infinite. So this is infinitely large, this quantity. And this is a case where, I mean, it's infinitely large, so you're going, given L, then you keep coming back, and this is where you get this MSD that, you know, it keeps doing that. Because you, I mean, any trajectory will come back to the origin at the same time. Yes?
The ballistic case is actually like going in a straight line.
Yes, yes, that's the ballistic case.
And if the T is, or Q of theta is constant, then it's going in
yeah, Q of theta constant, then this is the random walk situation. You're not going in circle. Random walk. No. Q of theta is the turning angle distribution. If it's random, the turning angle you choose, then you are.
Straight line. Also.
No. Then you are in. That's the case of the Brownian walk. So that's the case of the random walk. I mean, totally random walk, which is.
Okay. If it's Q of theta is constant but not 0, then you always going in a circle way.
Yeah, Q of theta is constant, but it has to be uniform. I mean uniform, so normalized to 1. Then you are in a situation where you have a random walker. So that corresponds to some value of t. Some value of t. And so this quantity is not infinite. And then you'll have this general situation. Now, the actual diffusive case, remember, because we have a speed, we have a real speed. Remember that if you want the actual diffusive case, you have always to make t going to 0, v sufficiently large, so that v squared t gives you a diffusion constant. So then, remember, we always have v squared t for t infinitely large, t infinitely small, v infinitely large, and this becomes the diffusion constant. So there is a little bit. But don't think about diffusion, just think about the animal as a speed, an average speed v, the animal as a turning angle distribution. So it's a bit of tricky math that you have to do to get the diffusive case.
Now the question is the fluctuations.
I mean, the damp oscillations.
What?
The damp oscillation, you mean?
The oscillation, yeah.
The damp oscillation. Well, it's different. Yeah, okay.
Okay. As depending, assuming t is constant. Okay.
Capital T constant, yeah.
Capital T constant. Depends on v over L.
Yeah, if you keep this,
Between v and L.
if you keep this constant, then it's the ratio of this.
Yeah. Is it optimal or increasing? I mean, is the oscillation increased with this ratio, or there is an optimum?
No, the oscillation keeps getting less and less damped as you increase that ratio. So there is a dependence, let's call it alpha. As alpha is getting larger and larger, then you get more, the oscillation are less and less damped. And in the limit alpha infinite, then you are in the ballistic case, and then. Now, of course, you don't have to be infinite. If you have a box sufficiently large and this animal is correlated, the other way. If you have a box sufficiently small and the animal doesn't have so much correlation, but that number is very large, then you have a lot of oscillation before it gets damped out. So that's why it's a ratio of a length scale determined by the correlation of the animal and the actual size of the box. So it's a ratio of two length scales. What time is it on?
5 minutes to 12.
5 minutes to 12. Okay. Yes.
If you have animal walking, its walk, can you, by its move, calculate the L?
Yeah, that's what I'm saying. Yeah, even without doing minimum convex polygon, through this method, indeed. That's precisely what I'm proposing. I mean, I haven't done in any data set yet, but this is what I'm proposing. You know, it was related to this question: why should I bother? I know about that this happens in the MSD when I have a bounded box. Aha! I said no. You bother because to determine what's the size of the home range, there are all these difficult issues, and the methods are always you wait long enough. I'm saying you don't have to wait long enough. If you capture a couple of those oscillations, then you can fit the model, and you get an accurate VT over L.
What is L in a complex shaped moment?
Aha, okay. So that's a good question now. That's why I have two geometry that I can tell you. The square geometry or rectangular geometry, I mean, they're similar. And there is a circular geometry. Now, if you have something which is very different from those two, then yeah, you're right. Then just take my paper, throw it away. I mean, no, in the sense, that becomes more difficult. But at least you have a sort of a null model you can use and see.
What you can do is, which direction, you have all kinds of, the boundary is changing. You can average over that.
Well, I mean,
you're choosing directions, X and Y. For in each direction you have different boundaries, right?
Yeah, but I think what he was, okay, I go to what he was saying, which is, I mean, he's right asking the question. No, if you have, I mean, if I have a home range which is like this, then of course I can think about a rectangle, and then I can use such a theory. Then if I have a home range which is like this, then of course I can about a circle. But now if you have something like this, I mean, then you have to rethink. I mean, okay, so then maybe I have a corridor here, then I have you know, so it's not, that's what I think he was asking. No? So which is a fair question, yeah. So.
Yeah, we deal with birds, they can cross it.
Yeah, I mean, then you have to start, I mean, be creative in some sense, no? So.
But you look at each point at the x length and y length.
Yeah, but then if you have correlation, yeah, I mean, if it's in 2D, you have correlation, that doesn't help. I mean, you really have to take into account the fact that it's 2D. So you can't decompose in X and Y. I mean, you can, but then you're not going to get the right fit. Yes?
You set different starting points to deviate it to square or rounds, and set in the middle of each shape the starting point.
Yes.
Then recalculate and sum somehow.
Yeah, but remember, what I was saying is that you can use this theory without knowing much about the boundary. If you know so much about the boundary, then don't, I mean, that's it. So then why bother? We mean you know so much. So then.
Yeah, but here you assume circular or round.
Yeah. So I'm saying that you have exact result over this quantity. Now, in the case of the circular, here you have a radius rather than L for the two geometry there, and yeah. Anything else?
The frequency has to do with the speed, right?
Yeah, it's this presence of this is precisely has to do with this. I mean, if you can be more quantitative. I just want to stop here. I mean, I can tell you more, but it's quite tough math. Okay, I mean, if what you saw the other days was challenging for you, I'm not going to show you this. But I can tell you how to use it. I mean, I can tell you that expression is just an infinite series. Just use it. So, all clear? Yeah, it seems so. Now, this is for the exercise of tomorrow. So I'll start since I have some time to tell you a bit now. This is the one that you may want or you may not want to do, which is having data, which is this rats moving in this circular arena. And I want you to create from a single trajectory the mean square displacement. Notice it's a single trajectory, and we have talked so far always about putting together trajectories starting at the same point. So something is weird, no? How do you connect the two? So I'm going to tell you why. How, at least. So I think I'm not going to ask you to fit the monster theory to those data, but I want you to understand how to create mean square displacement plot from a single trajectory. Oh, what time is it?
5 minutes after we asked you this time.
Oh, so I asked 5 minutes ago? Okay, so I thought I talked for... Okay, no, just to know. So I have half an hour at least, yeah. Yeah, plenty, yes. Well, okay, plenty. For me, I think it's plenty. Let's see. So, now, see how yeah. So let's forget about a second about boundedness, but just think about having a trajectory of an animal in unbound domain, and you have data point which keeps for a long period. Now, what we've been always talking about here is that we think about that you have many of these trajectories starting from the same point. And then when you do the simulation, you have the others, and then you put at each time stamp, you put them together and you get your MSD. But now what happens if you just have one?
Compare the displacement from the starting point, no?
But you have to generate many trajectories. So you have to find a way to generate many trajectories from one trajectory.
Find the right parameters of the equation that...
No. We are talking about real data. No parameters here. It's a real... Yeah, how do you do this randomization? So this is the key.
Bootstrapping. Under probability. If you have a long enough trajectory.
Okay.
Under distribution by the changing
you have a lot of data. You have
yeah.
You have the three different T's for...
Very good. So this is the right answer. So essentially you are close to the right answer. So what you do is that, okay, the assumption is that the statistics of the animal is not changing. It's always the same, whatever, correlated or random walk. And what you do is that you essentially, it's like the so-called time window averaging. So you pick a time window. Remember, these are observation discrete, no? So, I mean, there is a point here and so on. Okay, let me do like this, no? And then what I do is that I want to know on average, irrespective of where it started from, if the time window is one interval, I can just think about this interval or that interval or that interval in time. So the interval, so I forgot to say, this is useful when you have a sampling which is always regular. So then you have time window 1, you calculate there is a value for the displacement here. And there is a value for displacement here. So now the initial position is this one and then is that one. Then a different initial position, but then you have displacement there. And then you just slide it, that's why it's called sliding window. And so in that way, now you have, if I have a plot of time, this is a time window now, let's say 1. Suppose that this has 1,000 data points. So I'm going to have 1,000 value of displacement at time 1. You agree? So I would have, if I have to plot all this displacement, let's say, well, there is x and y here, whatever. But then, as I have it, and then if I want the mean square displacement, at time 1, I have 1,000 of those values, and I'm going to do the average. The same average as you do on the computer. It's exactly the same. So then I have an MSD here, at time 1, which I construct by having, now in this case, I have 1,000. Well, 1,000 minus 1. Okay.
You take a lot of trajectories that starts at different points?
Correct. I mean, I take a lot of trajectories. I synthesize trajectory in this way by putting a time window of 1. Now, this is time window 1, no? So then I'm going to have a value for this, whatever that might be. So there was a 0, which is you input by hand. Now you're going to have a value at time t1. Now, what happened at time t2? Well, now the window is of units 2.
Yeah, 500.
No, 1,000 minus 2.
you have
1000 minus 2, you stop. No. So yeah, no, it's not that bad. Otherwise you'll be already. So now a window of 2. So let me explode this so that you make it clear. So this is the first, this is the second. So the window of 1 was doing like this, now calculating this displacement and so on. Now the window of 2 is going to be this first data point. This is the second data point that connects these two. And this is going to be, whatever the, So that's why 1000 minus 2. So now we are going to have 1000 minus 2 value of MSD, if you're calculating MSD, to average over.
But now,
yes?
because you are always working with positive values.
Positive value of what? Of
Distance.
Yeah.
So you don't really need the square distance.
No. There is, in fact, I said, do whatever you want, but in this way you synthesize new data, new trajectories from one trajectory. Now, so far I've been talking so much about MSD, so that's why I'm just telling you about the MSD. I mean, you can do anything, You can do, remember that as you do this, you synthesize as if it's a new trajectory, of which you know what is a whatever, x0, y0, x1, y1 after time t2. So you don't have to necessarily do only displacement.
But actually it should be 500 because they shouldn't be overlapping.
Yeah,
well, that's not
be independent.
But I mean,
correlation.
But you always have.
No, but that's not why there should be. This is. I mean, there are lots of discussion about people that think that they're overlapping, non-overlapping. I don't agree, Ran, but I mean, I know. I mean, there are people. No, this is a way that.
Because of autocorrelation, you're saying?
No, because lack of independence of the data.
Yes, autocorrelation.
Yeah, but the
No,
whole
it's
point.
not.
That's how you calculate it.
Not autocorrelation, lack of independence.
No, but the point is that this data, of course, I mean, you remember. So the concept is the following: you want to generate trajectories which have the same statistical property of the one that you have. So you want to have that statistical property, and if the statistical properties they are correlated, then good, do it. So that you want them, because you are just synthesizing new trajectory in this way. You don't want to change, I mean, you're assuming that the statistical properties are the same. That's what the assumption to do that.
Essentially, you're picking turning angles from the distribution that the only distribution that you have is this one trajectory, so you're just picking from the 1000 turning angles or 999 that you already have.
Yeah. In some sense, yes, not exactly, because remember that your turning angle is going to be always like this, no? But then as you make the T1 is true what you said, but T2 you have something else. So
no, in T2 you just have less to choose from.
No, because turning angle is just because between two. See? You see? So at T1 is correct what you said, but at T2, so that's why here you are going to plot the MSD. Remember that as you do this is to plot the MSD. Now, if you want to, you don't need to synthesize more the turning angle distribution. You already know that.
But
at T1, you have all those, that representing. Yeah, so whichever. 3.
If you would plot the same graph, but instead of the MSD, you will have the sample size. So of course it diminishes linearly with the window size, because for the first one you have 999 and then 98. When it comes down to the longer segments,
very good.
I don't know, 700 measurements.
Yeah, so you're right. So there is a limitation of this method, which is, that's why I'm saying, to synthesize new trajectories from one, it has to be, first it has to be sampled regularly, fine, that it has to be a long one. Now, how long? Well, for example, if you're observing those features about the oscillation, then it all depends. I mean, I can't say a priori. It's hard to say, no? If you want to try to find those features fitting those parameters, it depends. So it's hard to say, oh, for that problem, pick, I don't know, 24 hours. It's very hard.
Because it depends on the inherent distribution of the error.
No, I mean, it depends on the question you have. It's only how long it should be depends only on the question you want to answer. Because he's right. What he's saying is that the number of data points on this plot of the MSD, or whatever other plot you're using by synthesizing this trajectory, is going to be more and more inaccurate, because you have less and less data points.
Would you get the same result if you take all your turning angles and all your step length, whatever, and you randomize them, and you make 1,000 of these trajectories from randomized data?
Yeah, you are going to get something which is very similar. Yeah, you're going to get something very similar.
And then, but then you don't have the problem of the accuracy towards the end.
In that case, you don't have the problem of the accuracy towards the end. Yeah, that's true. Yeah.
Okay.
You could do that as well. No, so this is more. It's like, I don't want to talk about even turning angle distribution. You see, as I do it, I don't even need that. Notice that as I do this exercise, I plot the MSD versus time, and then I come up, if I was looking about boundedness and so on, and then I come up with this value, so I don't even have to worry about what the turning angle distribution is, because I get a T, which relates to a turning angle distribution. Yeah. So this is, without going through that step, you just boom, because this is a, well, I say it's a simple code that you're going to develop to do this. I think it's a simple code. This is part of the exercise number 4, to do this time window. But the point is that you just forget about all of that, and you just look at the MSD as a time dependence, which you can interpret without, I mean, you know there is a connection, but you can, without thinking about turning angle distribution. Oh, yes, sorry.
If you have a certain reference point, it can be the boundary, if you have one, I mean the confinement, or some point of bias, the animal retractor. So you can't use this method.
Aha, wait. This is the part where I said unbounded space. Aha, wait. So I haven't finished here, eh? What time is it? Oh, no, that's a joke. No, that's a joke. That was a joke. Now, what happens with the confinement? Very good. Because now, what happens is that here, if you have unbounded space, any point of this trajectory is equally likely. There is no element where spatially you are forced to go back or do something special. So this you can only do if you actually have a theory. I mean, let's talk about the MSD to try to represent that. If you actually have developed a theory where the MSD expression, you remember this is going to be a function of the initial position. I mean, we were always talking about x not being the origin, but it doesn't have to. And time. You agree, no?
Now we are in a confined space.
We are in confined space. So there is a parameter here, let's call the radius or the size L, which is there. And then there is a parameter which is the speed of the animal. And then, if you want, there is a T, which is a capital T. But no, we don't know. No. But what I'm saying is that, I'm just saying, you can find this expression. But this expression clearly depends on the initial position. And now I do some magic, as I like to say. So, as you do this randomization, from one trajectory you get many. If you are in bounded space, then what you have to do on the theory to do the same that you're doing on the trajectory, because you don't know where the boundary is in some sense, no? But you just, yeah? So here you integrate over initial condition. Notice that on the trajectory, as you do it, you are always having a different initial condition, but now with reference to a box. Now there is a reference place. In the past, if it was infinite domain, it didn't matter. Now there is a reference box now. So now it matters. And so what you can do too much in the data because, well, if it's ecological data, you know where the box is. I mean, you don't, but in the theory, you just integrate over initial condition. And so what you do, you just do the dx naught for whatever the box here, minus L over 2. This is one dimension, you do that. And so you're going to have something that I might call F average, which doesn't have x naught dependence anymore. And this is the one you compare to exactly what you said, to that procedure that I showed you, which is the time window average when there is a box. So now you take into account where you are, because you are fitting with a theory where you have actually integrated over the initial condition, which is what you are doing here. But then it depends where you are now. Now, what the integration here, the probability that you have to take into account over where the initial condition is, if you know nothing special, it's uniform. So you're going to have this, you integrate, and you're going to have a 1 over L here, because it's for the initial condition. This is what the best to do, because...
Don't you need, if you have this track, don't you need to have a track which goes to all the points in order to do this integration?
Say again?
Don't you need, if you have one track and you have bounded space, but you don't know the boundary?
Yeah, you don't know.
So you need this track to go through all the points.
Yeah, I mean, in some sense, you're right, but you don't know. You know, remember, here you're trying to extract parameters on an ecological situation. You don't know where the boundary is. You don't know many things. So I'm saying that I'm just responding to what he was saying. Oh, but here you have to be careful. There's some special point here. Oh, yes, you are right. Now, if it's this the geometry is right, then I say we are going to fix the problem by picking the theoretical MSD expression, integrating all possible initial conditions, which is similar to what you're doing in some assumption that, you know, you assume that it's kind of spread out more or less. You know, that you have to assume that that's right.
A big track.
Yeah, that's right. That's right. Typically, a long track is, I mean, if you are in a bounded space, it's a long track. You know, it's gone more or less in most. Now, if you see, you know, the track that I've given you to look at, you know, this was just a 1/50 of that. I mean, if you plot all the data, it's all red. So I would have not given you data which are very sparse inside the box.
Can you repeat this? What are you integrating over?
So, do you remember that the MSD expression that I was telling you has always an initial position, initial starting point. You're plotting something starting from some value, x0. Doesn't have to be the origin. So the MSD, therefore, has the original expression for something in bounded space, a random walk in bounded space, which has some correlation due to t, capital T, starts with the position at x0. So forget about this part. So this is the MSD expression.
This is now for the time window average method, right?
No, this is a theory. Wait. This is I'm just telling you, this is a theory. I'm just telling you, there is an expression which is written out in some papers, which has this form. It depends on x0, t, and it has the parameter L, V, and T, or R, V, and T, depending which geometry you are.
Okay.
The expression depends clearly on the initial condition, no? And then you can plot this expression. You say, my initial condition is the origin, then let me plot it. And then you do this plot, which are typically, you know, this plot or whatever that plot, depending what's happening. Now, this expression depends on x0. Now, on the data, what you do, as you synthesize new trajectories, what you're actually also doing, you're changing your initial condition. So you better do this one on the theory as well.
Why does it depend on x0?
Oh, well, you always depend on your original. You know, it's a distance from an origin. I mean, when you compute the MS,
you're in unbounded space.
It's also there. I mean, it depends from a distance from an origin. No, in the unbounded space, well, it doesn't matter because, you know, it's unbounded space. At any point there is no important point.
Why does it depend when you're in confined space?
Well, because, you know, this point here, if you are here, I mean, you can't get out. So, I mean, the statistics of your movement here is going to be different of the specific moment in which you are there. I can't choose, you know, something special is going to happen there. Yes?
So when you are creating an endless number of initial points,
yeah.
You go only in one direction, only forward, or what about when you are on the trajectory? On
the track. Yeah. No, you go forward.
Only forward?
Yeah, I go forward. Why would you go?
No, because then you lose the information from behind. Forward.
Yeah, but it's a question that time window decides what you're talking about. So I'm going, I mean, if I go backward, I repeat some data, no? I mean, I think I don't understand the question. So, I mean, I go time window 1, I go forward, and once I'm ended, I've taken all the possibility into account. So for going forward,
x0 was the initial beginning, right?
Yeah. So, oh, you mean if I actually, as I'm here, then I come back. So therefore now I have an x not. Yeah, but this is eventually in the yeah. Okay, I understand now. In the MSD, since you are talking about the actual displacement, it doesn't matter. I mean, for something else may matter. Then you can actually use that going backward. Because then you're talking about the actual distances. I mean, remember, here you're plotting distances. So that case, then you're repeating yourself.
Maybe you can draw a path and explain how you do the integration.
The theoretical integration, but that means doing the math.
No, the path, not other.
Oh, do you want me to redraw the path?
Just the,
yeah.
To get the intuition.
No, to get again the intuition, yeah. So, I mean, there is one data point here, here, here. So then, you know, you have your trajectory. Oops. So, time window 1, I want to have a data point here on my MSD. I want to find the data here. So, time window 1, I calculate the distance starting from here to there. Then I have a different initial condition, and then I calculate the distance on this. Two data points. Now, 3 data points, 4 data points, 5 data points, and I keep going until I reach the end of the track. Time window 2, so first data point, second data point, third data point, fourth data point, and go on. Now, time window 3, and I always move 1, no? Yeah.
But what about the integrated?
Well, but the point, you see, notice, as soon as I do this, I mean, as I do this, now the initial condition is different. In this space now is important because it's bounded. I mean, again, remember there is some boundary here. I don't know where it is. And now this initial condition is important, no? So now this one is, how far is from the boundary? Okay, yeah, it's in the middle, doesn't matter. But no, when it's here, it's important.
But what in the process that you're in your computation, what is different from the unbounded space computation?
No, in creating this trajectory, nothing. That's what I'm saying. It's a theory that you have to, I mean, and I don't want to go into the details what happens to the theory. There are lots of cancellation there. But so, what I'm saying is that you have to integrate the theory because you can't do much here if you don't know where this boundary are. So then what you can do, you go to the theory, okay, let me take into account that in the theory. So I do the integration, and the simplest uniform of the space, this is 1 over L. So now I have an expression where I've averaged over initial condition. And now it's perfectly fine for me to compare to something where I've also averaged over initial condition. I mean, and seriously, as you do this average of initial condition, initially it's a double series becoming 1 series. And I can tell you if you want detail. But anyway, so it's pretty different, the expression. There are very different features. I mean, they still have oscillation, but you have different features as you reduce by doing the integration of x naught. Not dramatically different, but quite important difference on this, damped oscillation. So. Oh yes.
You can also use, if you have like a trail or a path that the animal follows, so it might not be straight, but the correlation is still follow the path.
Can you?
So here you have the initial condition of the turning the angle.
Yeah.
Takes this into account.
I couldn't understand very well. So you're saying that you have some sort of corridor. A trail is a corridor for me, no? Am I right? So if I have a corridor, so there is some confinement there.
If you look for a correlated random walk, you look for a straight line. But if the corridor is not straight, then you will miss this correlation between points. You will think you lost correlation while the correlation is with the path.
No, but I mean, if there is remember that this, what I'm all saying.
Confinement.
Yeah, but what I'm saying here, unless you have a complicated geometry, as your colleague back there was telling me, if it's a rectangle, we can deal with that. So if you do the things right, the theory together with the data will allow you to precisely predict if it's a rectangle, so Lx, Ly, so they're very different. You can get it. You can determine that. I mean, the expressions are more complicated because you have an Lx and Ly, but you can get that. So remember, this is the whole point, is that if there is a boundedness and the geometry is simple enough, you can find out what that is without going through minimum convex polygon, utilization distribution, and all these problems that methodology has. But simple enough geometry.
Was it ever compared, the minimum convex polygon?
No. No. Well, this has been out 6 months ago, this paper. I mean, so. And besides, I mean, you know, this is what I'm telling you can do. It's not written in that paper, so I don't know. It takes some time for people to understand what to do, especially if you see how monstrous expressions are there. But yeah, it's something I want to see the advantage. I mean, if you understood, do you remember? This is the exercise tomorrow. Today, if either I tell them what they have to do today. Let me see. Yeah, you can tell them. So let me tell you what the exercise number 3 today. It's simple, eh? Oh yes.
How do you average all the trajectories that you have? You did the one with window 1, so you have t plus 1.
Yeah.
And then you have t plus 2, or
and then you keep doing. And imagine that you have n data points. I mean, n fixes. Then window 1, you will stop at n minus 1 data points. Window 2, you will have n minus 2 data points here. Window 3, n minus 3, n minus 4, and so on. So you come to a point that, I mean, if you have a window of a size n, that doesn't make much sense, no? So you stop much before. You stop at n, when this is, let's say, I would say n half, because the n number that you have, this is the data that you have in this specific example. It's like 1 every 25 milliseconds, I think. So you have a lot of data there, but you know, of course, the computer does it for you. So I think you can go a few minutes. So. But
then you average maybe T1 with the T1 of the other window, because it's not the same time. In the T1, you have, let's say, 1.25, but in the bigger window,
no.
Step is larger.
No, the bigger window, remember, the bigger window is your averaging. So once you choose, so you choose a window of time, and then you get a set of values, random values. Then you do an average, and you get 1 data point here. Then you choose a window of time 2, whatever that unit is, in whatever, millisecond, and then you average, you do that average over now this, no? And then you get another data point here. And then you do, so if you haven't understood, I have to explain again, because this is part of the exercise, so ask me.
No, I have a question about this. The larger your time window is, the less and less certain you are of the.
Yeah, you have more errors.
MSD. Is there a way to express this, like confidence interval, or?
No, so the confidence interval on that is only related to, I mean, I'm not going to ask you because it's a little bit tricky, but anyway, it has related to the detection, I mean, the value of the detection of your X position here. Okay? So I haven't developed yet a method to say, so this is the confidence you should use. So I am not going to ask you to do it, since it's not completely clear to me how to. And it's essentially related to, I mean, if you want, there is an error bar here.
Yes.
And then, but since you are taking all of them into account, it's not clear if I can just put that, you know, so it's, if I, yeah, I don't know, because probably it has to do with the 4th moment, and so the square root of the 4th moment that you might do, because you're plotting the MSD, which is the 2nd moment, so then you have to do the variance of that, which is probably, but I'm not completely convinced myself, so I don't want you to do that part of the exercise, but you're right, it's a fair question, yeah. So I think it's a 4th, I mean, the square root of the 4th moment, but yeah.
What happens if you one time do what you said with the time windows, and then the next time you start from the end and go back? and you calculate the MSD. So then on the second time you have like many repetitions, and then you kind of...
I mean, if you're just calculating MSD, you're going to get the same result, because you're just calculating the distance that you know.
Oh, no.
If you're doing something else, no, maybe different, but just because he was asking before.
Yeah.
No? It's all clear how to do the time window average? Now, just the last few minutes, the exercise number 3 today, a simulation. So just simulations, not looking at any data. So I want you to plot the MSD for a random walk. So in continuous space. So first you have a distribution of turning angles, because that's what you always need to do the simulation, which is going to be uniform. And you do simulation in, and I would say let's do the square box first. So square box, and actually let's use always the square box. So that's not, because otherwise the circular geometry the code gets a bit more complicated. You have to take into account the 90-degree reflection. Now here you just have the x and y component, so it's easy. Now I'm going to tell you one more thing. So this is the exercise 1, 3.1. The exercise 3.2 is that you actually pick 2 distribution of turning angles. One which is, well, should be normalized, sorry. One which is more peaked maybe, and the other one less peaked, because I want you to see 2 values where you see that you go from lots of oscillation, more damped, and then So I want you to see exactly what I've just told you. Now, when you do simulation with boundaries, you have to always be careful how you deal with boundaries. This is always a tricky business. So the best way to do it, so that your code is simple, is that,
This is still 1D?
No, 2D, just do straight 2D. Yeah. I think I wrote 1D, so I'm going to give you the, I just thinking, this night I was thinking it's better to just go straight 2D. So just wait to see the last version of this PDF. So I'll have some modification now. Now, how do you do the simulation when you reach the boundary? Because this is the only thing that you're going to input in your simulation you've done so far. No? So the best way, there are technicalities involved in my answer, but I don't want to tell you why, but just please do it. Okay? So you reach, imagine you have a box. You come here, and now you draw a distance from an exponential distribution, I forgot to say. So exponential distribution, step length. And you come here, then of course it's a moment that you select a distance and an angle. Oops, and you find out you're out. So simply keep it put. Just leave.
Ignore the data.
No. Keep the data. Just keep the data and keep it put. Then you redraw, and then if it still stay there, it's not going to stay forever there. No? But so there shouldn't be any problem. Unless you have a lot of correlation, then you can get stuck, no? Because you keep going. But so if you are in that situation, you put a lot of correlation, then as you draw a random displacement, then you're out. Then if you have a lot of correlation, then choose an angle at random from a uniform distribution, so then you have a choice to get out. No?
The last point, what was you suggested once you...
No, so the suggestion is that you reach there, and then if you suddenly find out that you're going out, so you made an if loop, easy, just keep it put. So in some sense, it's as if he's going out, and then he's coming back.
So draw a new angle distance?
Yeah, so once he's come back there, so the time has advanced by 1 unit.
You do count the time.
Yeah, you do count the time. I mean, technically speaking, he's actually going against the wall and coming back. No, it is displacing, but it's going against the wall and coming back.
When you calculate it, it's zero displacement.
Yeah, there when you actually calculate it says not displaced in that because you're using a discrete time, no? So it's some technicality about because of comparison with theory. But yeah, just do it like this. So the only thing I'm saying that you may find yourself stuck if you have a lot of correlation, and then suddenly, by chance, the guy is there, and you keep selecting a distribution because it was coming from here maybe, and then you keep trying to select one, and so you have to wait so long to get an angle which is, turning you back. So then in case, so if you don't put too much correlation, then you just, it sits there, then you do it a few draw, and then it goes away. No? So this is only that difficult. Just be careful about that. I'll be around. I mean, so, but I don't let you there. Eh? So what do you say?
Is it going to blow?
No. So is it clear for what to do in the exercise 3?
So 3-1 is
3-1 is the random walk. So sorry, just here. 3-1 is this one, and 3-2 are these two. So I want to see the different damped oscillation.
If each one of them you want to see the MSD.
And the MSD clearly. So 3 MSD plot and the code for the two. Well, for the two cases, there will be one case because you take the von Mises distribution, you put the parameter right, you get the uniform. No, so it's one code.